Hello, I am Anand Jain from Hanumangarh, Rajasthan. I welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our subject electric circuit, we'll discuss electrical resistivity and understand the factors which affect electrical resistivity such as mechanical work, change of temperature, addition of impurities. So let's begin this English video for class 12th physics about electrical resistivity. In our one video of Ohm's law, link given in end screen with this video, we have studied that resistance is opposition of conductor to the current flow, and that opposition demand proportional voltage application for circulation of current through the conductor. And for an ohmic resistance where physical condition of conduction remains the same, the current and voltage are proportional to each other and their relationship is a straight line passing through origin as shown here. And in this characteristic, you will find that slope is everywhere the same and the resistance is inverse of the slope of this characteristic, and we can say the ratio of applied voltage and flowing current is the same at all position, and resistance is a constant and its value doesn't depend upon applied voltage or current passing through it. But if we study another relation of resistance with geometry parameter length, cross-section area and a material constant resistivity, then we'll find that this resistance is directly proportional to length of conductor, inversely proportional to area of cross-section, and it also depends upon resistivity. Now this rho resistivity is also known as specific resistance, and for a conductor of length 1 meter and cross-section area of 1 meter square, the value of resistance is resistivity, and resistivity is an inverse of electrical property conductivity, and conductivity depend upon number of free charge carrier per unit volume and mobility. Now the mobility is related to drift, moving, free electron velocity and applied electric field. In conductor, when we apply voltage and that voltage establish an electric field, the free electron start drifting in one direction with a certain velocity, and that drift velocity is directly proportional to applied electric field, and the proportionality constant is called as mobility. And this mobility depends upon collision property of material concern, and mobility is directly proportional to time between two collisions, that is called relaxation time. If collisions take longer time, then we'll find that with the same electric field, longer interval is available to accelerate electron in a particular direction, and that increase drift velocity or mobility and conductivity, and the resistivity get decreased. So we'll find that this resistivity depends upon two parameter. One is number of free charge carrier per unit volume, that depends upon nature of material, and the another parameter is mobility, that depend upon internal structure and physical conditions, temperature like of conductor. And today in this video we'll study how different factors affect the resistivity of a conductor. Temperature is the most important parameter which affect resistivity, but we will start with effect of mechanical working and impurity on resistivity first, as both effects can be explained on similar lines. Now the rapid cooling after heating is called hardening, and such hard-drawn copper got higher amount of resistivity as compared to a material which is annealed. Similarly, now the addition of impurity will increase resistivity of material. Pure electrolytic copper, which is 99.99% pure, got least amount of resistivity, roughly 1.7 into 10 to the power minus 8 ohm meter. When in a pure copper alloying is done with nickel 10%, then resistivity will increase by about 10-12%, and similarly when impurity nickel amount is increased to 25%, resistivity become almost double in comparison to pure copper, and further increase of impurity will further increase resistivity. Now in both case, rapid cooling after heating, that is hardening, or in addition of impurity, the regular atomic crystal structure of metal get deformed, and in deformed crystal, when applied electric potential starts drift motion of electrons, more collisions will take and collision time will decrease, and decrease of relaxation time will decrease mobility and conductivity, and reciprocal of conductivity, resistivity will increase with both hardening and impurity addition. To increase mechanical hardness and strength, we perform hardening operation or add impurity in pure metal. Many a times impurity is also added to reduce cost of material. But the reverse process, where after heating, cooling is performed very slowly and gradually, then irregular crystal structure get modified into regular format, and this process is called annealing, and this will increase flexibility, malleability and softness of material, and at the same time it reduce resistivity. So a pure electrolytic copper, if also annealed, then it will have the least amount of resistivity compared to hardened copper or copper with some impurities. Similarly, when we refine material and remove all sort of impurities, it will refine crystal structure, reduce number of collisions, increase time between collision or relaxation time, mobility and conductivity, and decrease resistivity and resistance. So when we need softness, flexibility and increased conductivity, we use pure electrolytic grade conductor material with annealing done on that. Temperature is most important parameter which affect resistivity of conductor and semiconductors. Let's first study effect of temperature on resistivity of metallic conductor. In metallic conductor, when we increase temperature, it will increase thermal motion of free electron, which is random in nature and which cause collision among thermal moving electron and drift moving electron. And increased temperature, when increased thermal motion, that increase number of collisions, and these collisions are basically represent opposition of conductor against current flow of drift moving free electrons, and increased collision will increase resistance of material. We can understand when we increase temperature, thermal velocity of free electron increases, that increase number of collisions, and when time available for acceleration before collision reduce, this will reduce drift velocity of electrons, and that is represented as decrease of mobility, and decreased mobility will reduce conductivity, as conductivity is directly proportional to mobility when number of free charge carrier are constant. And in metal, when you increase temperature, it will not change the number density of free charge carrier, and when mobility has decreased, that has decreased conductivity, and inverse of that, resistivity and resistance get increased. So temperature and resistance got identical relation. When temperature is increased, resistivity and resistance of metals get increased, and in vice versa, when temperature is decreased, the thermal velocity get decreased. This will reduce amount of collision, and time between collision or relaxation time has increased, that increase mobility and conductivity and results in reduced value of resistivity and resistance. Again, the temperature change and resistance change got identical pattern. Temperature reduction will reduce resistance of metallic conductor. Pure metallic conductor, copper, nickel, platinum, they have higher temperature sensitivity for resistance, and when temperature is increased, the resistance gradually and continuously increases in all pure metals with high amount of magnitude. In copper and aluminum, the change of resistance or resistivity with change of temperature got a little non-linearity, whereas for nickel, from minus 50 degrees centigrade to 250 degrees centigrade, the change of resistivity and temperature got almost linear behavior. And for platinum, resistivity change and temperature change got a great linearity in a very long range. And this property of nickel and platinum, having linear change in resistance with change of temperature, is used in temperature measurement. Whereas some alloy such as constantan and manganese, they have a very little small change in resistance when temperature is changed. Now the constantan is a copper nickel alloy with copper 55 to 60% and nickel 45% or 40%, and it is also known as Eureka. And its name constantan represent that its resistivity or resistance remain constant with respect to change of temperature. But constantan with copper got a thermo EMF problem. So a better alloy material, improved one, is manganese, and in manganese we use 84% copper, 12% manganese and a little amount of 4% nickel. In these alloy constantan and manganese, atoms are already in quite disorder due to addition of impurity in material, and they show higher initial resistivity, and with increased temperature, the additional disorder which will take place won't make a significant change. So resistivity or resistance won't have a significant change with change of temperature in constant and in manganese. So pure metals got higher sensitivity for resistivity change with respect to temperature change, and alloy got less sensitivity of resistance change with respect to temperature change. In carbon, which is a non-metallic conductor, and in some semiconductors such as germanium or silicon, when we increase temperature, resistivity or resistance decreases, which is just opposite to metals. And the key reason for this opposite behavior of resistivity change with respect to temperature change in carbon and semiconductor is that there exists covalent bonding in these materials. And when we increase temperature, the number of covalent bonds which are in broken state increases, and these increased number of broken covalent bonds increase number of free charge carrier, and due to increased charge carrier density with increase of temperature, the conductivity, which is product of free charge carrier density and mobility, will increase. As increased temperature slightly reduce mobility by increased collision, but the number of free charge carrier by increased temperature increase by a great amount, and the product of charge carrier number and mobility increases. And as a result, when we increase temperature, resistivity and resistance sharply decreases in carbon and semiconductor material, and the vice versa take place when you decrease temperature. This will reduce number of free charge carrier density, and that reduce conductivity and increase resistivity and resistance. So in semiconductor, change of resistance and change of temperature got opposite nature. Increased temperature reduce resistance, and decreased temperature increase resistance, which is opposite to behavior of metals. Change in resistance value with change of temperature is mathematically expressed in terms of temperature coefficient of resistance, abbreviated as TCR, temperature coefficient of resistance. If initial resistance is R0 and after delta T temperature change, if resistance become RT, then the change of resistance is final value minus initial value, and it is observed that change in resistance is directly proportional to change in temperature if other parameter remains the same. So if we double the amount of temperature change, then the amount of resistance change also get doubled. Now this value of resistance change also depends upon initial value of resistance. If other parameter remains the same, if initial resistance is made 10 times, then the change of resistance in tenfold increased resistance also become tenfold. And if we combine these two proportionality into single proportionality, then we can say change of resistance is directly proportional to product of initial resistance and amount of temperature change. And this proportional relation can be converted into equality using a constant, and that constant is known as TCR, or temperature coefficient of resistance, abbreviated here by symbol alpha. And this alpha, which relate amount of resistance change with temperature change, also depends upon temperature, and for a particular temperature the magnitude of alpha is constant, and relation of change in resistance, initial resistance, temperature change is given by this yellow highlight. And from this relation we can explain TCR as change of resistance per unit of initial resistance per degree Celsius temperature change, or one can define TCR as it is that amount of resistance change which will take place in 1 ohm resistance by temperature change of 1 degree Celsius. In metals, when we increase temperature, resistance will also increase. So delta R and delta T both got identical signs and the ratio is positive. And for pure metals, small amount of temperature change can result in good amount of resistance change. So alpha is slightly higher in magnitude, whereas for alloys such as constantan or manganese, for temperature change, amount of resistance change is negligible small. So for constantan and manganese, TCR value is very small. And for semiconductor and carbon, the change of temperature and change of resistance got opposite signs, and the ratio TCR is negative for semiconductor and carbon. In place of change in resistance, we can write a difference of final resistance and initial resistance, and if initial resistance is taken to other side and brought out as a common, we can say that if initial resistance is R0, TCR is alpha, then after delta T temperature change, new resistance will become RT, and this relation in blue frame is very important, which relate initial resistance, final resistance value with TCR and temperature change. For the same metallic conductor of the same material and same geometric parameter, the voltage and current relationship for two different temperature T1 and T2 is as shown by these two linear relations, brown and blue. We have to find out which temperature out of T1 and T2 is higher in magnitude. Now resistance is voltage to current ratio, and for comparison, if we make denominator current function the same, the corresponding numerator values for T1 temperature is V1 and for T2 temperature it is V2. So for two different temperature, the two value of resistance R1 and R2 is given by these expressions, and for same current V1 is higher in magnitude as compared to V2. So V1 upon I ratio is higher than V2 upon I ratio, and R1 is greater than R2. And we know for metallic conductor, the amount of resistance will increase when temperature is increased, and definitely when first resistance R1 is higher, that means first temperature T1 is higher, and we can say T1 is higher than T2. Now the same question can also be solved as when current is on vertical axis, the resistance is inverse of the slope of VI characteristic, and T2 temperature characteristic got higher amount of slope and lesser amount of resistance. So we can say T1 is greater than T2 in this example. This numerical example will explain that there exists a significant change in resistance value with change of temperature in pure metals, and it is given that at room temperature condition, which is at 20 degrees Celsius, the resistance of copper winding used in a fan is 100 ohm, and during working due to losses when temperature of winding is increased to hot conditions of 100 degrees Celsius, then what is the hot resistance of copper winding? And it is given that at room temperature 20 degrees Celsius, the TCR temperature coefficient of resistance for copper is 0.004 per degree Celsius. This numerical figure 0.004 per degree Celsius looks very small, but it is not in actual practice, as it is change of resistance per ohm per degree Celsius. Now in this question we are given that at 20 degree Celsius resistance is 100 ohm, TCR is 0.004 per degree Celsius, and delta T change of temperature in this experiment is from cold room temperature condition 20 degree to 100 degree Celsius. So this change, the difference of two temperature is 80 degrees Celsius, and we know that change in resistance, the difference of final and initial resistance, is directly proportional to change of temperature or initial value of resistance, and proportionality constant is known as TCR. And when we shift initial resistance to other side, then resistance at increased temperature is given as initial resistance 1 plus alpha delta T, where alpha is TCR given 0.004, delta T is change of temperature from 20 to 100 degrees Celsius, 80 degrees Celsius, and initial value of resistance at 20 degrees Celsius is given 100. And when we multiply 0.004 by 80 degree temperature change, this will become 0.32, and our new hot resistance at 100 degrees Celsius will become 132 ohm, and there exists a significant 32% increase in resistance when a resistance increased from cold 20 degrees Celsius to hot 100 degrees Celsius in this copper fan winding. In this example, it is given that at room temperature 27 degrees Celsius, resistance of a heating element is 100 ohm. Now we have to find out operating temperature of heating element. If its resistance is found to be 117 ohm at hot conditions, the TCR temperature coefficient of resistance for heating element material is quite small, 1.7 into 10 to the power minus 4 per degree Celsius. In fact, heating elements are made of some alloy like nichrome having a small value of TCR, so that their cold and hot resistance won't have a significant difference. Now given figure are cold 27 degree Celsius resistance is 100 ohm, hot resistance is 117 ohm, and TCR is 1.7 into 10 to the power minus 4 per degree Celsius. We know TCR is change of resistance per unit of initial resistance per degree amount of temperature change, and here TCR is given 1.7 into 10 to the power minus 4 per degree Celsius. Hot resistance and cold resistance difference is 17 ohm, cold resistance is 100 ohm, and we have to find out hot temperature, whereas cold temperature is 27 degrees Celsius. So the difference of two, hot temperature and cold temperature, T minus 27, is given as this difference is 17, and when this side is shifted from numerator, it will go to denominator side, and numeric simplification results in change of temperature equal to 1000 degrees Celsius, and this will make hot temperature 27 1027 plus 1027 degrees Celsius. So small value of TCR results in a very small change in resistance even with good enough change in operating temperature. This numerical example is very important from examination point of view as it involves a significant technical issue that this TCR value is a temperature dependent parameter, and here in this question for two comparison we'll take the same initial resistance condition or same initial temperature condition so that we can use the same value of TCR in two comparisons. Now in this question it is given that a resistance of a platinum wire which is used in a platinum resistance thermometer at ice point is 5 ohm and at steam point it is 5.23 ohm. Now platinum is a pure metal which got a very linear and appreciable change in resistance with change of temperature, and as it is indicated here from 0 Celsius temperature of ice at steam point condition 100 degrees Celsius resistance has changed from 5 ohm to 5.23 ohm. Now this thermometer is inserted in a hot bath and the resistance of platinum wire is found as 5.795 ohm, even higher than steam point resistance. That means this hot bath temperature is higher than 100 degrees Celsius. We have to calculate the temperature of bath. So here it is given that at 0 Celsius resistance of platinum wire is 5 ohm, and at 100 degree it is 5.23 ohm, and at hot temperature T, which we have to find out, the resistance is 5.795 ohm. We know change of resistance is directly proportional to initial resistance amount of temperature change and proportionality constant TCR. So from 0 to 100 degrees Celsius resistance become 5 ohm to 5.23 ohm. TCR at 0 Celsius is say alpha, which is not known to us, and 0 Celsius resistance is 5 ohm, and temperature change from 0 to 100 degrees Celsius is this much. Now for second comparison again we take initial temperature 0 Celsius and initial resistance again 5 ohm, but temperature change is T minus 0 and resistance nu is 5.795. Now we won't know alpha. This problem can be solved in two ways. From one expression we can calculate alpha value, TCR value, and we can substitute that alpha in second expression, or we can do another thing. We'll just take a ratio, and when we take a ratio, now the change of resistance in first condition and change of resistance in second condition, as TCR and initial resistance is same, become a ratio of change in temperature in first condition and change of temperature in second condition. So in one condition, when temperature is changed from ice to steam position 0 to 100, the resistance change is 5 to 5.23, that is 0.23 ohm. And in second condition, when temperature is changed from 0 to T, the change of resistance is from 5 to 5.795, 0.795. So ratio of change of resistance become a ratio of temperature change, and numeric calculation results in the temperature of 345.6 degrees Celsius. Pure metals like platinum and nickel got linear and appreciable change in resistance value with change of resistance, and they are used in resistance thermometer where we measure change of resistance in platinum wire or nickel wire and obtain the change in temperature. Now certain alloy like manganese or constantan have very small value of TCR. So in these alloys with change of temperature, the change in resistance is negligible small. So such alloy material, constantan and manganese, are used in measuring instruments. They are used as multiplier resistance in voltmeter or standard resistances of bridges or potentiometer wire, where we need such standard laboratory resistances which won't change with change of temperature. Whereas we also use thermistors, which are composite oxides of manganese, nickel, cobalt, magnesium, etc., and they form a powdered mixture with certain binding material, and they have a very high value of TCR, usually negative, and due to this high value of temperature coefficient of resistance, a small only 5 or 10 degrees Celsius temperature change can change manifold change in resistance value. So such thermistors are used in sensitive temperature measurement and in temperature related process control applications. Hopefully this video has explained all factors which affect electrical resistivity, and now you know how mechanical working, hardening or annealing affect resistivity, and you can also calculate change in resistance by change of temperature using the concept of TCR. Our other learning video of the same playlist will enhance your physics understanding and improve your scoring ability. If you found our work useful, do share it with your friends. Happy learning. Thank you very much.